All right, what's going on, everybody? Today we're doing another LeetCode video. This problem is called count good nodes in binary tree. So we're basically given a binary tree and they want us to count the number of good nodes in that tree. So that's a good nodes, that's not, it's not really a standard, metric for a binary tree. So what is a good node? So a good node in the context of this problem is any node that doesn't have a value that is greater than it between itself and the root node of the tree. So let's look at, so we can see that all of the good nodes in this tree, for example, 1 are blue. So let's look at every single node and see why it's a good node or why it's not a good node. So this first node 3 is going to be a good node because it itself is the root. So there's no node in between itself and the root that is greater than it. So it's got to be a good node. All right, so let's look at this left node. Now this left node we can see is not a good node because the value of the root node is greater than it. There is a value between itself and the root node that is greater than it. So it is not a good node. So what about this 3? Well, if we check the path to the root node, we can see that there's a 1 here. We can see that there's a 3 here. Neither of those values are bigger than 3. So 3 is going to be a good node. 4, there's no value that's greater than it between itself and the root node, so it's going to be good. 5, same thing. There's no greater value. This 1, however, if we go back toward the root node, we can see this 4 is greater than the 1, this 3 is greater than the 1, this 1 is obviously not a good node. So yeah, that's pretty much the idea, or I mean, that's the definition of good node versus not good node. So let's go ahead and get into this problem. I'm going to use a recursive depth first search for my algorithm. I would highly recommend, very highly recommend watching my video on right side or binary tree right side view. If you have a good understanding of that problem, I almost guarantee you can come up with a solution for this on your own. But nevertheless, let's get into the algorithm walkthrough. So basically what I'm going to do is I'm going to do a recursive depth first search. I think I already said that, but nevertheless, we're going to go in first to our root node, okay? And we're going to have a metric, right? We're going to be passing in a value into our depth first search that we're going to call greatest. And it's going to be the greatest node that we have seen on this path to this point, right? And we've got to keep track of this, basically because this is going to be our metric to determine at each node whether or not it's good or not, right? So initially the greatest value we've seen is going to be equal to the value of that root node itself, so that's going to be 3. Okay, so we're going to ask, is this node less than the greatest value we've seen? No, it is not. So this has to be a good node. So our good nodes count, we're going to C++, so we're going to do a plus plus, incrementation of our good nodes value. This is going to jump up to 1. So we now have 1 good node. Okay, so we're going to do a recursive depth first search we're going to pass in the left child node first. So let's go this way. The new greatest value that we have seen will be the max of this node and whatever the other greatest value was, so it's just going to be 3. Okay, so is this node value less than the greatest value we've seen? Yes, it is, so it's not a good node. Not a good node. We don't really have to do anything other than just not increment our good nodes counter. I'm going to put an X here because this one is not good. And okay, so let's continue with our depth first search. We're gonna go left again. We're gonna take the max of this and then the greatest node we've seen. It's still gonna be a 3. Okay, is this value less than that 3? No, it's not. So this node is good. We're gonna increment our good nodes by 1. So we have a 2 there now. Okay, so at this point we would be popping all the way back up because once we get to, by the way, if we see a null, the first thing we're gonna do before anything is check, okay, is this node we're at null? because like this one down here would be null. If it is, we're just going to return, right? So that way we pop back up in our recursive call stack. Okay, so now we're going to search right. The greatest node we've seen so far is going to be 3. Okay, so is 4 less than that 3? No, it's obviously not. So that node is good, and we're going to have 3 good nodes at this point. Okay, we're going to search left now, because we're always going to search left first in this algorithm, because we're going to do the recursive call on the left child first. Doesn't really matter, but that's the way I'm going to do it. So just to keep things consistent here in our walkthrough. So the greatest value we've seen now, the max here is, it's going to go up, because the max here between the greatest value you've seen and this node is 4. So we're going to have a 4 here now for the greatest value we've seen. Now, is 1 less than 4? Absolutely. So we're not gonna increase our good nodes counter. That's all we're gonna do. But to visualize that further, I'll just put an X, because this is not a good node. Okay, so we're gonna search this way finally, and we can see that the greatest value to this point will be that 4, and 5 is not smaller than 4. So we've got another good node, and the answer here is going to be 4 good nodes. And we can see that the ones that were not good were basically just numbers that were smaller than preceding numbers in the path toward the root. Right, or numbers that have nodes in between the root and itself that are greater, right? So there's like multiple ways you can kind of look at that, but nevertheless, let's get into the code. Actually, first, before I get into the code, the time and space for this problem is going to be, since it's a recursive depth first search, the time is just going to be big O of n, where n is the total number of nodes in the tree, because we have to visit every node once. And then the space complexity is also pretty straightforward. It's just going to be big O of h, where h is the height of the tree, because our recursive call stack takes extra space, and that scales corresponding to the height of the tree. Technically, it could be big O of n if the tree was heavily skewed, but we're just going to say big O of h, because that's really the average case there for the space complexity. So let's go ahead and get into the code here. Not too much code to write. We just need an integer for our number of good nodes. We also need to write another, like a separate recursive function that we can call. So we're gonna have a number of good nodes here. At first it'll just be 0. We need to go ahead and count those up with our recursion. So we'll just say depth first search. This will be a void function. So we're gonna do depth first search on our root node. We're gonna pass in the greatest value we've seen so far, right? We don't have a variable for that, but the greatest one we've seen technically at that root node will be whatever the value is there. So, and we know that we are going to have at least one node always. So we can always count on having a node to pass in here. Even if there wasn't, this algorithm would still work, because it would just return at a null node without incrementing num good nodes at all. But anyways, good to think about that. So so we're gonna have a root val, and then just the num good nodes for that last parameter. Okay, and then we can just return that num good nodes once the recursive function is done executing all of those recursions. So let's go ahead and make that a private function, and it's going to have a void return value. Again, we'll call this depth first search. We're going to have a tree node pointer to a tree node for that first parameter, and then we'll have the greatest value we've seen so far on that path up to that node, and then we'll have the number of good nodes by reference, because that's kind of like a global that we're updating. Okay, so the first thing we can do is check if that tree node is null. If it's null, we are obviously just going to return, right? Because we don't want to do anything at a null node. There can't be a good node there anyways, right? Because it's null. Okay, so the next thing we'll do is use that metric that we discussed. So if the current node's value, so tree node value, if that's going to be ever less than the greatest node we've seen so far, then we know that we don't have a good node, right? So we actually want the inverse of this to count our good node. So when tree node val is greater than or equal to the greatest node we've seen so far, then we can increment the number of good nodes that we've seen. Right, okay, and then after that, we just want to do our recursive calls. So we'll call depth first search on tree nodes left child, and then we also want to set the greatest, update the greatest value before this. So, but we know we're passing in the greatest, so I'll just get this part over with. So, and then that global count for the number of good nodes. So we want to do that on the right child too. So let's get that out of the way. And we also need to update the greatest value before we pass it into those functions. So the greatest value is going to be the max of whatever the previous greatest was, so whatever it currently is, and then whatever the value of that current node is that we're at. So that's how we're going to update that greatest, and that's pretty much going to be it for the code. So let's go ahead and submit this. Hopefully this video helped you understand this problem better. If it did, please leave a like and subscribe, and I'll see you guys in the next piece.